Yeah.
Okay, so let's start today's seminar. It is a pleasure to tell you that we have here Professor Hans Ludwig from the Observatoire at Paris-Meudon. Professor Ludwig got his PhD in Germany in 1992. After that, he has enjoyed quite a number of postdoc positions in different countries. And since his PhD, Professor Ludwig's interests are dedicated to the radiation-hydrodynamical modeling of stars. In 2005, he joined the staff for a 4-year position at the Observatoire of Paris-Meudon with the goal of studying the cosmological impact of the first stars. And this is the topic of his talk today. So thank you very much, Professor Ludwig.
Thank you for the kind introduction. Buenas tardes a todos. I'm afraid this is also all what you hear in Spanish from me. The topic that I'm going to talk about today are radiation-hydrodynamical model atmospheres across the HR diagram. So it's a little bit broader to what you said in the introduction. It's not only metal-poor stars, but they will play a prominent role. Yes. An overview. I have a problem. I have to decide which slides I use to point at, so I will use the left, perhaps the right-hand side. That's easier. Let's see. Yes. So what can you expect? So my role in this CIFIST Marie Curie Excellence team studying the metal-poor stars is the generation or production of 3D model atmospheres used for the chemical analysis of these stars. And during the course of the CIFIST projects, we have been working on covering as much of the HR diagram as we computationally could afford up to now with these kind of models. I'm going to talk about this coverage of the HR diagram. I will say some words about the 3D radiation hydro code that we are using, which is called Cobalt. A few words about the subsequent spectral synthesis, which is necessary for the ultimate comparison of spectral features of stars with predictions. Present the status of the CIFIST, which I call the CIFIST model atmosphere grid, how far we have been able to cover the HR diagram with these kind of model atmospheres. And then I would like to dive in, as time permits, in the number of applications in which we have used these models. One is related to the oxygen abundance in the binary star CS22876-032. If you can't remember this number, I can't it either, despite I've worked for some time on it. But what's important, it's a binary star, and it harbors the most metal-poor dwarf stars currently known. And this makes the object particularly interesting and has some implication for the overall understanding of the galactic chemical evolution. Another application is related to the lithium-6 abundance in extremely metal-poor halo dwarfs. And we did a case study of a particular halo dwarf called HD74000. And the outcome of the study is, say, a negative one in the sense that we cast some doubts on all measurements so far obtained for the lithium-6 abundance in these stars. It has some repercussions on Big Bang nucleosynthesis that I'm going to point at. It was difficult for me to decide what kind of applications I would like to show, so I had to leave out some interesting topics, which I would at least like to mention. One is related to the determination of effective temperatures of late-type stars by using Balmer line profiles. We have been starting a study using 3D models along these lines. I've been, over the last 2 years, on and off, repeatedly working with a student, Elisabetta Caffau, on the solar oxygen abundance. This is a long story in itself, and you might have heard that there has been quite a debate over the last years about the correct value of the solar oxygen abundance. And I just summarize here that our promoted value based on 3D, latest generation 3D model atmospheres is 8.76 plus minus 0.07 dex. And for the non-LTE aficionados among you, I would like to point out that half of this error bar comes about from the impact or ignorance of the non-LTE effect on some of the atomic oxygen lines that we used. An interesting subject that we in the CIFIST team have been also recently working on is the solar abundance of hafnium and thorium. This is precursory work that we have been doing for using this pair of elements for the radioactive dating of stars, something that becomes more and more now in the mainstream of cool star research. And last but not least, something that I dubbed the microvariability of solar type or late type stars. What I mean by this is that convection at the surface of a late type star produces an imprint in form of granulation. And the stochastic change of this random pattern leads to residual brightness fluctuation, even in integrated light of stars, like the sun. For the sun, it's about 40 ppm, so it's on a very low level, hence microvariability. However, these days, with the first satellite missions, the Canadian MOST mission and the French ESA-COROT mission, are now able to measure these residual brightness fluctuations in late-type stars, and it is interesting to compare model prediction with these brightness fluctuations actually measured. But as I said, I leave this out. I just throw these keywords on you in case you would like to have later on some more in-depth discussions on this subject. I would be happy to have later discussions on this. I should mention that I'm only here for today, so this afternoon is still available. So in case you have further questions or are interested to discuss things. Just to give you a brief overview what I'm talking about, this is an artist's view of a star like our sun. This is in fact the sun cut open, so the energy generated by thermonuclear fusion in the center of the star is transported by convective flows in the outermost 200,000 kilometers and ultimately radiated away by electromagnetic radiation at the surface. A visible imprint of this convective flows taking place at the surface is a solar or for stars stellar granulation, which is this kind of stochastic pattern familiar from the sun, which has, in the case of the sun, a typical spatial scale of 1,000 kilometers and evolves on a time scale of, say, 5 to 10 minutes. Important point here that I want to make is that this surface convective pattern is very small scale relative to the global scales of our sun, which allows to model this kind of flow pattern in a local fashion. And these are the models that I'm talking about are mostly of this kind, being a small Cartesian simulation volume encompassing the optically thin or the transition between optically thin and optically thick regions in the surface of a star. And it is, as I said, a very small subvolume. Okay, some words about the 3D radiation hydro code that I'm using for this purpose. It is dubbed CO5 cobalt, short cobalt. Why CO5? Well, it stands for the conservative code for the computation of compressible convection in a box of L dimensions. With L could be 2 or 3, so it can be 2 or 3D simulations. I admit it's a little bit of a contrived acronym, but it's what we came up with. The main developers are Bernd Freitag and Matthias Steffen, and a variety of people have contributed to the development efforts. Among them, Sven Wedemeyer-Böhm, now in Oslo, Jorrit Lennartz, also in Oslo, Werner Schaffenberg, now in the US in Michigan, and myself. What the code does is solve the HD or MHD equation coupled to the equation of radiative transfer. The HD or MHD part is solved using approximate Riemann solvers, which leads to a rather low intrinsic dissipation of the numerical scheme. So meaning good resolution for the number of given grid points, and also making the numerical scheme rather robust, especially in the presence of shocks, which are usually ubiquitous in late-type stars like the Sun. The wavelengths, the radiation field is treated in rather detail. It is the full geometry, non-local geometry is taken into account, including the wavelength dependence of the radiation field by a multi-group approach. And also the equation of state is handled in rather realistic fashion based on a tabulated version of an equation of state. In latest years, we implemented further physics in the code, depending on the problems of the problems we were interested in, related to the kinetics and transport of molecules and dust grains, describing for example, the non-equilibrium chemistry of CO in the solar photosphere and chromosphere, or also the dynamical effects on the ionization of hydrogen in the solar chromosphere, or of which I show later on some examples, the formation of dust grain in brown dwarf, very cool stellar atmospheres. The code stands out since it, by its very good conservative properties, it's strictly conservative up to a numerical round of errors in mass, momentum, and energy. Since one is only modeling a very shallow part at the very top of a late-type star like the Sun, not fully modeling on the complete convective envelope, one has to have a certain means how to deal with the in- and outflow of material in this simulation domain. So one needs open boundary conditions at the bottom, and also to allow, or say, get the little reflections of waves at the uppermost boundary, one needs some open boundaries also at the top to allow waves which are generated by the turbulent convection in the deeper layers to leave the volume with as little reflection as possible, to have not an unwanted feedback effect onto the deeper layers. The sidewise boundaries are simple. They are just periodic boundary conditions. I should say, and I will show an example of this kind, that Cobalt is not only able to handle these local box models, modeling a small piece at the stellar surface, which are informally dubbed now as box in a star models, but also the inverse one, the star in a box models, meaning putting a complete star in a three-dimensional domain. I will show later on in one example of this kind of application. And the result of all this is a statistical realization of the hydrodynamical flow from the subphotospheric up to the chromospheric layers. So you have to think about these models in some sense as a Monte Carlo simulation of the flows. It's not directly simulating a concrete situation, but representing the statistical properties of the flows. Okay, the topic is radiation hydrodynamical models across the HI diagram. I wanted to show one, say, example, an extreme example of two models showing convection. This is, in fact, the emergent radiation, as one might potentially observe, would be able to observe if one could resolve the surface of the corresponding stars. These are two extreme examples of such models. On the left-hand side, you see here surface convection in a cool white dwarf, where the box size is about 7.5 kilometers here. On the other hand, you see the surface convection in a red giant, where the box size is 23 solar radii. So it means you can conveniently put the sun in one of these convective cells. So, and this is possible today. So showing the codes this code has reached a sizable or good level of robustness, and it can deal with quite different parameter regimes. So the scale ratio here is of the order of 10 to the 6. I will not talk more about it, but I just wanted to flash this up. This is one example as a star in a box model, which is an example, again, of the apparent radiation, here color-coded in red. So darker colors means cooler. This is the convective envelope in a spherical geometry put into the put into a three-dimensional Cartesian container and is supposed to represent something like a red supergiant, taking, for example, Betelgeuse as a role model. So it is the complete convective envelope, except the very core of the star is not resolved here. So this is treated by an inner boundary condition. As I said, this is just an example of things that one could also do. Okay, and I will show in a moment the stars that the CIFIST group is mostly interested in, which are mostly hotter main sequence stars. But I would also like to point out that there are efforts underway to work towards lower effective temperatures. I have to say, it's a pity that Rafa Rebolo couldn't in person attend, but he explained to me that this is where the money is in the future. Not so much brown dwarfs, but planets. This is where one should go. And at least I'm trying to work my way slowly to this money area. So I'm mostly talking here about brown dwarfs. And also here, first M dwarfs. I'm involved in co-supervising a PhD project related to the line formation in M-type atmospheres and main and pre-main sequence stars conducted in Germany at the University of Göttingen, and also involved in a model conducted by Bernd Freitag in Lyon in France related to cloud formation in brown dwarf atmospheres. And what I would like to show you here are two just videos showing very initial precursory trials that we did to see how the coupling of convection and cloud formation operates in these stars. Sorry for sitting down, but I have to operate the computer now here. So let's see whether I can bring up the first video. Yes. Okay, what you see here is the amount of dust present in a two-dimensional model in the surface layers of a brown dwarf of an effective temperature around 1800 Kelvin. So this is, if you want to think about it as a two-dimensional slice, this is the horizontal direction, this is the vertical dimension. And what is color-coded here is the amount of dust present in the convective flow. Brown dwarfs have extended convective envelopes, so material deep from inside the stars, also transporting energy by convection outwards. You have a flow up. Stuff is cooling at the stellar surface, which is located about here, and then sinking back. What you see here is these filamentary structures are, in fact, these downflowing regions, and you see here this bubbling. It's like a thunderstorm during a summer day in which material reaching the temperatures at which dust can condense, all of a sudden, below a threshold temperature, form dust grains, block to some extent. No, that's. Which button? Thank you. Cools here at the surface, lingers for some time. I should say linger, it's like rain. The dust grains feel the pull of gravity and have the tendency to sink back. And there's a competition between the upwards whirling motions of convection, leading to the condensation of material in the cooler layers and the gravitational sedimentation of the material down back into the star. This color coding is a little bit misleading since it is logarithmically. I selected this video since one is nicely seeing these filamentary downflows. In fact, the density of condensate of dust in these layers is very low, so that in fact there's essentially nothing there. It's only the strong enhancement due to the logarithmic scale that makes it visible. In order to give you a little bit more realistic view of how it's actually looking, I wanted to show another video of the same kind, but now with a linear scaling, which gives you a better visual impression of what is actually going on. You don't see the photospheric convection anymore, but you see how the dust is rapidly condensing here, stays for some time, and then advected back inwards into the star. The two horizontal lines mark the optical depth unity, so indicating that under these conditions, one just sees the upper cloud decks in this brown dwarf, and this line marks the 1/10 optical depth. Okay. So far for that. Now coming to the model grid that CIFIST has been working on. This is the state of affairs after about 2 years of operation of the CIFIST group, indicating in a spectroscopist's HR diagram, meaning surface gravity of a star is a function of effective temperature, the kind of models we have been able to produce so far. This is a rather, so all in all, we are now at a model count of about 60. Green means the models are completed. Red are ones that are at the moment running. This roundish thing marks the location of the sun. And I should say that each of the gravity effective temperature pair is split into 4 sub-squares, indicating stars of various metallicity, ranging from upper right, solar metallicity, and going then down in factors of 10 to minus 1/10, 100, 1,000 solar metallicity. Since CIFIST is interested in metal-poor stars, it was for us important to have a sequence of models of decreasing metallicity. So all in all, we have now about 60 models. You might say that doesn't sound like much, but to my knowledge, it's the most extended model of three-dimensional hydrodynamical model atmospheres existing to date. And to give you a feeling about the computational effort necessary, it's about, depending on which parameter we are talking about, dwarfs are a little bit simpler than giants. So for a dwarf model, we need typically 3,000 CPU hours on a one processor PC-like machine, which goes up to about 20,000 or even more hours for giant models. Okay, it's a little view on one of our workhorses. We are doing these calculations on a cluster-like machine. This is we invested about 50,000 euros. This is our cluster, since we are living in France, and we called it Godot, since we have to wait usually a lot to get our models done. This is a cluster consisting of 14 individual PCs, basically, running double-core, double-processor AMD Opteron processors. So what we are doing there in terms of parallelization is not that we use a cluster as a real one unit, but we are putting each individual stellar parameter combination on one of the boxes and run the models in parallel using the 4 compute cores in each of these boxes. Okay, besides the hydrodynamical model as such, one needs afterwards to use this or to make contact to observations for the interpretation of spectral lines. One also has to have a spectral synthesis package at hand, which allows one to use these 3D models to generate line profiles. And I think to most of you working at this institute, this is not big news what I'm showing here, but I just wanted to show some sort of giving you a flavor of what is going on. So what is so special about these three-dimensional models? What makes them different from standard 1D model atmospheres? Well, we have this convective granulation pattern on the surface of a star, and if you look at high spatial resolution with a spectrograph at the various locations, one would get something like shown here. I should say that the color coding corresponds, so color corresponds to location. So you see how the spectral properties, here I selected just more or less arbitrarily an iron 2 line changes across the granulation pattern. You see here in this bright inner granular region, you have a bright continuum. This is here absolute intensity versus wavelengths expressed as Doppler velocity with respect to the laboratory wavelength of this line. You have a bright continuum and a strong line, deep line core. And the line appears a little bit blue shifted due to the fact that usually the inner bright parts of granules correspond to upflowing motion. Similarly, if you look here, for example, at this green spot, it's a dark downflowing region, so you have a dark continuum. The line looks pretty, say, distorted due to the line of sight velocities along this line of sight, and it is redshifted. Of course, we have usually not the luxury to be able to observe stars like the sun spatially resolved. But nevertheless, due to the non-linearities in the line formation process, even in disk-integrated light, residual effects of these variations of the line profiles across the stellar surface are still present and are not, by definition or by construction, not be possible to catch by standard one-dimensional models. An important further outcome of these calculations is that the classical 3 parameters of micro and macro turbulence need not to be specified, since the hydrodynamical model provides the full information about the velocity field. These parameters are not free anymore, but outcome of the model calculation, so one has not the necessity to specify micro and macro turbulence in the line formation problem anymore. Okay, so far for the, say, theoretical precursor. Now I wanted to go a little bit into applications of these kind of models, starting with the... Yes? Yes, yes, to some extent. You know, these models have a long history, of course, so it's not the first in the generation of various models of this kind. But we have been, for example, looking at the center-to-limb variation of the continuum in the sun and find a respectable correspondence for a theoretical model. We have also been looking at individual lines to be able to reproduce the line shape, including line bisectors of iron lines. And we are still working on trying to compare, for example, the granulation contrast with observations. But as you perhaps know, it is not so easy to measure the granulation contrast with high, say, fidelity. So there's still a little gap between the theoretical predictions and the observations. But to some extent, I think these are also observational shortcomings due to problems of getting the point spread function and scattered light correctly modeled in the observations. Yes? Yes. Yes. Yeah. Yes. Yeah. But this question is, of course, also very relevant for metal-poor stellar models. As you will see in a moment, there are differences to 1D spectra, to 1D models are particularly pronounced. Perhaps we should come to this. And this is still an area where I think a lot of extra additional work is necessary for validating these kind of models. Okay, this is work, in fact, primarily led by one of the people here in the audience, Jonay Gonzalez Hernandez. It is related to the determination of the abundance of oxygen in this extremely metal-poor binary at a metallicity of about minus 3.7 dex relative to the sun. As I said, the most metal-poor dwarf known at the moment. And Jonay did a detailed analysis based on 3D model atmospheres of oxygen OH molecular lines in this star, and finds that in comparison to 1D classical analysis, the abundance, the oxygen abundance coming from these OH molecular lines is different by 1.5 dex for the primary component and 1 dex for the secondary component. So you see the difference in the resulting abundance is substantial between 1D and 3D models. I should say that I picked here a particularly extreme case since, of course, OH lines as being produced by a molecule are very temperature sensitive. And as we will see in a moment, they are also formed pretty high up in the atmosphere, where differences between 1D and 3D models are particularly pronounced. Interesting outcome is if you apply, going here from 1D result, this, or I should have said, this is the oxygen over iron ratio as a function of iron contents of these two binary stars. Here now, compared to results of other authors kind of stemming from giants and dwarf stars. The important point of the alternative measurements is that they are not using OH molecular lines. I should have said, in this extremely metal poor star, we have not the luxury anymore to have different, a variety of oxygen abundance indicators at hand anymore. We are left with OH lines in the ultraviolet, so there's nothing else we can use anymore in dwarfs. The point here is that these results are stemming from the forbidden oxygen line at 6,300 angstrom, which is much more robust against 3D effects. And the interesting result is applying these large corrections that the overall trend of this binary now falls quite nicely into the general trend we see here. And for you, for those among you who are interested in the chemical evolution of the galaxy, you might have followed the dispute whether the oxygen to iron ratio is flat over the evolution of the galaxy or there is a slope. In this case, you have to read the iron content as a time axis, meaning we are looking here back in time at the early phases of the evolution of the galaxy and here towards the present. I don't want to go into the issue of studying the chemical evolution of the galaxy. I just wanted to give you a feeling why there is this enormous discrepancy in the abundance of oxygen coming from this OH lines between 1D and 3D models. So I just wanted to show, this is, I should have said, these are F-type stars, the two components. Well, yeah, one is a late type F, the other one is a mid F-type object. And in fact, these are now two models sitting at the effective temperature and gravity of the binary star. And they are just different here in the metal content. At the left-hand side, this is a solar metallicity simulation. On the right-hand side, you have a 1,000 solar metallicity simulation. And I guess for those of you who are rarely looking at these things, you might say, this looks more or less the same. And I would to first order agree. The convection looks very similar in these two stars, or in these two parameters, for these two parameters. And in fact, also the typical velocities look pretty much the same, which I try to show here. This is a convective velocity on a horizontally averaged and also averaged in time as a function of optical depth of the two 3D models. The black one is the solar metallicity, blue one is the subsolar 1,000th solar metallicity model. Also in comparison to classical 1D atmosphere models where the convection is modeled with the help of mixing length theory. And you see that the 3D models, and comparing to 1D, show a strong overshooting of the convective motions actually being convectively stable here in the deeper layers into the atmosphere. But basically, one would say, okay, the overshooting and also the magnitude is pretty comparable. So also in this sense, they come out to be pretty similar. However, what comes out quite differently is the response of the mean temperature profile in the stellar atmosphere being subjected to these overshooting motions. With these overshooting motions, there's also, of course, energy transport associated. And this energy transport tries to modify the stratification towards an adiabatic, purely adiabatic stratification, while radiation prefers to establish radiative equilibrium in these layers. And the question is now, who wins? What is the balance between this adiabatic cooling of overshooting motions entering the stellar atmosphere in comparison to radiation, which tries to establish radiative equilibrium? And this is, I try to show here in this graph, this is the outcome. I should say that the solar metallicity model is shifted up by 2000 degrees for clarity. So what is shown here is the horizontal average of the temperature as a function of optical depth for the solar metallicity, and again the subsolar metallicity star. In the solid line is the 3D result. The dashed line is the 1D result. And in the 1D models, by definition, by construction, radiative equilibrium is assumed in the optically thin layers, or which are not affected by convection within the framework of mixing length theory. And as you see that in the solar metallicity case, the deviation of the temperature profile from the classical 1D result is pretty small. It's not zero, but rather not very big. There's a sizable difference of up to, it increases with that, up to 2,000 degrees. No, wait a moment, 1,000 degrees here at the lowest optical depth. The OH molecules, which are producing these OH lines used for the determination of the oxygen abundance, are formed pretty high up here in these optically thin regions, and differences of a couple of 100 degrees up to 1,000 degrees produce this large difference in OH abundance, density of molecules in these layers, and finally, as a consequence, the strong difference in the line strengths and resultant oxygen abundance. Okay, I have 4 minutes left, so I think I have to hurry up if I want to go through the story of the lithium isotopic ratio. Perhaps I just flash some points up for later discussion, since the story is pretty complicated, so I'm not sure whether I'm able to convey the message in the few minutes that are left. But let me try. This is our present knowledge about the abundance or the evolution of the lithium. Or let's not talk about, again. Hello? Okay. Let's talk about not the evolution, but this is the functional dependence of the lithium abundance of lithium-7 and the lithium isotopic ratio as a function of metallicity in stars, showing here for lithium-7 a plateau-like behavior, which is called since it was discovered by Monique and François Speed, the speed plateau. And here recent measurements by Martin Asplund and collaborators of the lithium-6 abundance. And he found a similar behavior of a rather flat dependence of these are these blue dots, of the lithium-6 abundance with metallicity. There are several aspects here that I don't want to go into, but predictions from the measurements of the cosmic microwave background, together with considerations related to the nucleosynthesis and the Big Bang, predict for the lithium-7 abundance this level. This we would expect asymptotically at very low metallicity, meaning very early phases in the galactic chemical evolution for the lithium content. And you see there's a sizable gap, about a factor of 2 to 3, in between those, which are presently not understood and not fully explained. Even worse, the story gets for lithium-6, since the Big Bang nucleosynthesis predicts essentially no production of lithium-6 whatsoever. This means if we can take these measurements seriously, there's a serious problems either with the Big Bang nucleosynthesis, or there are not so well understood production mechanisms in the early phases of the galaxy or stars which are able to produce lithium-6. But in any case, it's important to understand this, and at the present, mainly by the measurements by Asplund and collaborators, but also by Smith at collaborators 1983, 1986, Querelle 1997, and Nissen 1997, there's a belief that the lithium-6 isotopic ratio relative to lithium-7 is 0.05. So 5% of the lithium is sitting in lithium-6. Well, the measurement of lithium-6 is a very subtle, difficult matter for a spectroscopist, and I try to explain this here. As I said, we're conducting a case study for a metal-poor halo dwarf sitting at a metallicity of about -2, putting it here. Looking at the, trying to determine the lithium-6 abundance. And the strategic spectral feature that one is looking at is a lithium resonance line at 6708 angstrom, shown here. The observations are shown here by these points with error bars. I come in a moment to the theoretical consideration here, but you might say in first place, oh yeah, this is a pretty wiggly bad spectrum. But I would like to point out that this is a spectrum as good as one can expect it to get. There were about 20 hours of HARPS observing time going into the measurement of this profile. 20 hours HARPS, extremely high spectral resolution, about 110,000. Resulting signal to noise of 600, and also an extremely good wavelength calibration of this line was possible due to the usage of HARPS. As I said, the line is pretty complicated. It is a duplet, has two main components. Each component has a number of hyperfine subcomponents, so it's a pretty complicated feature. The two main components of lithium-7 are shown here by these green dashed lines. This is a main component, and here's a secondary weaker component. And now the components which are associated, also lithium-6 has the same, at least main structure, the duplet structure, but the lithium-6, since it's only 5% by present measurements, are with this nominal value of 5% here are shown here. These weak blue features. One difficult point is that the stronger feature of lithium-6 falls exactly on the weaker feature of weaker feature of lithium-7, and it's practically impossible to disentangle those. And what one is left is this little blip of extra absorption which comes from lithium-6, on which these measurements are based. Okay, now, how do you measure in this kind of noisy or imperfect spectrum this kind of weak extra absorption? Well, this is done by fitting, of course, synthetic profiles to this line. And now, I should say, this investigation was headed by Roger Querelle, who came up with a pretty clever idea, namely not using theoretical models, since who is believing in this crap? We do this purely empirically. And to this end, he has been looking at iron lines in the spectrum and identifying iron lines which have very similar formation properties as the individual components of this lithium-6 or lithium-7 line, meaning that the distribution of absorbers in the atmosphere corresponds to the expected distribution of the lithium absorbers, meaning the line should also show, except for thermal broadening, the same asymmetry as the lithium line. Now I came up with the keyword, which is important in the whole business, namely the fact that up to now in all investigations of lithium-6, the intrinsic line asymmetry was usually neglected. And the idea of Roger Querelle was to investigate the effect of the line asymmetry on the effect of the lithium-6 measurement. And what is shown here by this empirical line profile, which is a composite of 5 lines which were identified in the spectrum as being similar to the lithium, individual components of the lithium line, is a degeneracy between spectral line asymmetry and lithium-6 content. What is shown here in red is the extra absorption that one expects from this weak lithium-6 component in comparison to the effect which comes about by the line asymmetry by looking at the line as is and mirror imaged and take the relative to the line center and take the difference. And it turns out that the asymmetry of a line largely mimics the extra absorption which one expects from lithium-6. And already on this basis, one starts to be a little bit skeptical whether analysis which ignore the line asymmetry come up with a reasonable measurement of the lithium-6. Now we tried to fit now the empirical profile with these other empirical iron profiles and came up with a situation that we can generate lithium content between 6% if we keep the wavelength scale fixed as the good wavelength calibration of HARPS provides. If we allow a global wavelength shift, we come up with a result that the iron lines produce would lead to a prediction of no lithium-6 whatsoever. But if we are using a symmetric profile, a classical analysis, and leave also the shift free, we end up with a wavelength shift of 420 meters per second and a 2% per level of lithium-6. Okay, this is the empirical result. What do we believe in the end? And at this point, again, theory comes in. And just as my final slide, I would like to show the difference of a 3D line profile between LTE and non-LTE. And it turns out that, first of all, with the non-LTE, okay, I should explain that this is one component of the lithium line showing from a 3D model the line asymmetry, the asymmetric component, once in LTE in black, red in non-LTE. I should say the main non-LTE effect is a reduction of the line strength by about a factor of 2. This is scaled out here. Both lines are scaled to the same depth. But what is striking is this is a line bisector for both lines. The lines show a different redshift. First of all, they show a redshift, and they show a different redshift in LTE and non-LTE, and a different line width. And taking this together, that the non-LTE profile predicts a shift of 300 meters per second of the line relative to the laboratory wavelengths, it becomes now plausible why we need this shift of 370 meters per second to get the best fit for the empirical line profile, and also with the result that we can't detect any lithium-6 in this star. And as a final result that we obtained here is that we say that this particular star doesn't show any lithium-6 in the full 3D non-LTE analysis on a level with a precision of plus minus 2%. So significantly below the 0.05%, which was now around from the measurements of Asplund and collaborators and others before. Okay, I leave you now with this pretty complicated story. I think there's more to say about it to understand it, and thanks for your attention.
There's time for discussion and questions. Okay, Arik.
Hans, how do you solve radiation transfer in a slowly moving atmosphere?
Sorry, can you
have a dynamical atmosphere,
yes,
right? How do you solve radiation transfer equation? How do you solve radiation transfer equation in this atmosphere, in a dynamical atmosphere?
Are you now speaking about the 3D model atmosphere or the posterior line formation
3D.
problem? The hydrodynamical
yeah, exactly.
model.
You have a velocity field.
Yes.
In 3D.
Yes.
And then you solve radiation transfer.
Yes.
For this atmosphere.
Yes.
For dynamical atmosphere
yes.
in 3D. How do you do that?
The velocity field is for the radiation transport in the hydrodynamical model atmosphere as such ignored. So there are no effects of the velocity field on the radiation transfer in the 3D model as such. Yeah. For the posterior line formation calculation, of course, since one is interested in details like the line asymmetries, the effects of Doppler shifts are fully taken into consideration. So One is we are using long characteristics. If you want to talk now really technical.
I mean, it's in a co-moving frame. How do you do?
Oh no, this is not co-moving frame radiative transfer. We do the radiative transfer in a Eulerian framework. So, is this answering the question?
Yeah. Okay.
So
yes. Yeah. Okay. Now. Yep.
For each point, the thermal broadening is taken into consideration. The net shift with respect to the laboratory wavelengths is taken into consideration to evaluate the line opacity at this particular point, and then integrated. I said it wrongly. It's not long characteristic. It's a formal integration, formal integration simply along the line of sight. And this is done for vertical directions, looking vertically into this three-dimensional data cube, and also inclined direction for modeling the center-to-limb variation to get, in the end, the disk-integrated spectrum.
Okay. Yeah.
More questions? Okay.
I have recently heard about very low metallicity stars of about metallicity -5.
Yes.
And do you know if there is a lithium abundance study in these stars?
Oh, that's a good question. I think so, but I'm not sure about the values which came out of this. But I would like to point out that one should be careful about the statement of metallicity in this context. They're extremely, or what people usually call hyper-metal poor stars that you're pointing at, are hyper-metal poor in the content of iron. But they have a very high abundance of CNO elements. Yes. Mm-hmm. So they are not very extreme when it comes to this. I mean the CNO elements and others. So the overall metal content is much higher than in these objects. It's only that the iron content makes them such extreme objects. But I forgot what the present idea about the lithium content is in the stars. But I'm pretty sure that people have been measuring this.
Okay.
Honai, do you know? They did not find anything. Okay. Okay. Yeah. Oh. Mm.
Okay.
Okay. Two questions. First is, how do you treat rotation and differential rotation, which is very important for these subtle effects? And
yes.
The second have to do with the oxygen abundance that you presented in the first slide. I noticed that you gave a value which is higher than the value given by Aspen.
Yes.
Could you comment on that? So differential rotation and oxygen abundance.
Differential rotation is ignored here, but I'm convinced that differential rotation is not important on this level here. These stars are considered to be very slow rotators, and they are very old and have spun down to almost immeasurable V sin I. This star has a let's say it this way, the line profiles we tried to match here, we had to add an extra broadening of about corresponding to a velocity of 1 kilometer per second, which is close to the nominal resolution that we expect for the HARPS spectrograph. And everything extra would be then related to rotational line broadening, but the level is so small that it's, I think, insignificant here for this kind of problem. Not to talk about differential rotation. But I have to say, in principle, we added, I think, a part of this 1 kilometer per second in the form of rotational line broadening, as rotational broadening, in the even quite detailed fashion, taking into consideration the center-to-limb variation of the line profiles and so on and so forth. But I think it's irrelevant for this lithium-6 question here, since the rotational speeds are too small. Yes, the solar oxygen abundance. This is, as I said, a long story in itself, and it has been haunting me on and off, and still is going to haunt me for some time. But the value that I've been quoting here in my first slide is an outcome of looking at the atomic oxygen lines. Here, this 8.76. And I should point out for the people who are not aware of the story, the presently promoted lowest value by the work of, again, Asplund and collaborators is 8.66. So we are 0.1 dex promoted value, 1.1 dex higher. And since the sun is pretty well observed, this is a significant difference, which would be not so important for these extremely metal-poor stars. We have been only looking at atomic lines, not molecular lines, which Asplund did, and he said to some extent it's coming from his also low abundances from the molecular lines, which leads to the overall low oxygen abundance. However, my feeling is that the 3D models even 3D models are not quite there to be reliable enough in the temperature structure to be able to predict the line strength of molecular lines in the sun on this level. What we also did is, and I'm surprised that people have not been doing this before, we have been not only looking at one observed spectrum of the sun, but took 4 high-quality atlases of disk-integrated light, 2 disk-integrated light spectra and 2 disk center spectra, to take more into consideration the available observational material. Funny enough, we also have, when remeasuring this line strength, came up with a different conclusions from what have people obtained before. Our equivalent width in a number of lines is bigger than before, especially for strong lines, since we put more, I would say more care in exactly modeling the far wings of lines, which leads systematically usually to larger equivalent width. So, half of the error bar, I said, comes from uncertainties of the non-LTE corrections. Asplund and collaborators ignored, or I should say the question is revolving about collisions with neutral hydrogen atoms, which are theoretical and experimentally not very well constrained. Asplund and collaborators opted to ignore the collisions with neutral hydrogen in their non-LTE corrections altogether, which leads to very large or rather large NLTE corrections, and these are pushing the overall oxygen abundance down. We opted, due to our ignorance, to use intermediate value traded in between the extremes, which are discussed, which leads to this value. If I had used Asplund's value, we would have ended up at a value of 8.73, so only 0.07 dex higher. Had we used a larger collisional cross-section, our uppermost value would have ended up at 8.79, plus minus 0.04. As I said, some of the systematics is buried here in this 0.07 dex error bar. So if one would be able to better pinpoint, or theoretical or experimentally, these collisional cross-section, one could at least beat down the error bar by at least a factor of 2. No, not only the oxygen triplet, but the NLTE corrections are particularly important for the oxygen triplet lines. I was talking about the all atomic oxygen abundance indicators, meaning oxygen triplet lines, the 2 forbidden lines. There's one bar at 615 angstroms and 3 in the near infrared, which can be. Yes. We have 9, all in all. But only atomic, not molecular lines. Yes. Cobalt, 12-bin radiative transfer model of the sun. As I said, and
it could be that the difference. It could be then that the difference with Martin Asplund's determination is because of the different two models.
Yes, this is part.
It's not so much about the collision with hydrogen or not.
Yes, that is possible. And it is, I think, perhaps surprising enough, I suspect that it's not only the model atmosphere, it's also the associated spectral synthesis code which starts to matter. I've seen independent evaluations of the oxygen abundance using the line strength and even the model, the 3D model or mean 3D model that Martin has been using. And people have been using different spectral synthesis codes and end up with numbers which are of the level of 0.05 dex different, solely by using a different spectral synthesis code. So there are also more systematics buried in the overall analysis than just the underlying 3D model atmosphere. Yeah?
Hans, one more question. If you compute the contribution functions for OH lines in 1D models,
yes,
you will see that they formed very deep in the atmosphere. They are not formed in the upper atmosphere.
Oh, yeah.
It's very easy to make a test. You can chop the upper parts and compute every time the new atmosphere, and you will see that it doesn't change the abundancy and the line strength. It's very straightforward calculation.
Okay.
So nobody has done this for the 3D models, but everybody claims that these lines are formed in the upper atmosphere. I don't know how. You agree, yes, with me? Yeah, exactly, yes. No, not the triplet, OH lines.
OH lines.
I'm talking about OH lines.
Good point. So I will check this. I have
discussed this with Schnitt and with Lambert, with everybody, yes, and everybody agrees with me. They did the test and they found the same.
Okay, and if you say not so high, what do you mean in terms of optical depth?
I mean, if you chop the atmosphere down to a log tau -1, you will find the same abundancy or the same line strength.
What?
Yeah.
So that means that my whole explanation here should be taken with a grain of salt, and it's in fact the temperature inhomogeneities which make the lines look different. But I will check this. I have the contribution functions in my spectral synthesis code still on my disk, so I can take a direct look at it.
Okay. Okay.
So, yes.
Electronic transitions.
Yes.
Calculated in LTE.
In LTE, yes.
We'll have to investigate this assumption also, I think.
Yes, this is a very good point, but who knows better than you that there has been very little work been dedicated to the non-LTE effect in molecular lines. So I would be very happy if some NLTE specialist would do, yeah. I was hoping for you that okay. Yes, but a good point. That's true. That's a matter of uncertainty.
Okay, you have been talking about hydrodynamical models, and I mean there is also magnetic fields there. And
yes.
The question is that well, it's now clear that whenever you have a velocity field, a plasma with all these complex motions, you also have an associated magnetic field, a kind of turbulent dynamo, something like that.
Yes.
Would it make any impact on? This is something that should be considered, or any comment?
Yeah, so that's a good point you are raising. Also, Javier has convinced me that there is turbulent dynamo generally at work on a level which is kinematically becomes or dynamically important, and this would, to some extent, mean that the good correspondence of the 3D model with the center-to-limb variation might be, to some extent, fortuitous. This is, of course, worrisome, and I think it's a good point to follow up on this. Of course, I didn't emphasize, say, very much the problems that I still see in these kind of models. But, for example, I've seen that the convective energy transport in the solar model looks as if it's working a little bit too efficient in the sense that what the stellar structure people call the entropy jump from the surface to the adiabatic deep layers comes out too small. One can measure the adiabatic value of the adiabatically stratified bulk of the solar convective zone today pretty precisely from helioseismology. and one compare it with predictions that one can also derive from these kind of models. And there is, at the moment, for my best solar model, a discrepancy of 10%. In the sense, as I said, that convection works too efficiently. One could speculate that magnetic fields might put some sand in the convective machinery, making convection a little bit less efficient to bring the correspondence between the surface models better to the expectations of the overall thermal profile of the solar convective envelope.
Do you foresee having magnetic fields in these models soon, or?
Yeah. You know, especially here in the Institute, there are a lot of efforts going in this direction. And I would say my own main interest, since I'm now mostly working towards covering the HI diagram with these kind of models, it is not my main thrust that I would now like to put most efforts in. But certainly to obtain a higher degree of fidelity at some point, I think this is necessary. Since the similarity of the convective properties, I mean, these convective cells look, except from scaling properties, pretty much similar to the sun. One would expect that processes operate very much similar to the solar convection. So if the local dynamo is at work in the solar convection, I would expect this to work in all these stars as well. But it's a lot of work.
Yes, I have a question. You've mentioned that there is a discrepancy in the abundance of the oxygen element using the 3D models as compared to the 1D models.
Yes.
But what about other elements, like the light elements, beryllium, boron, or other elements like carbon? Do you find similar discrepancies? Because these lines are formed in regions where the models predict different behavior?
That's a good question. Ronald, do you remember the values for the different lines as well now for this binary work? Now, have you looked at carbon, nitrogen, oxygen? Oxygen, yes, but no.
We are planning to do 3D corrections to calculate 3D corrections for all the elements in this binary star, but we are still in process, so I cannot tell anything.
But one light element here is lithium, and if in effect, if you do the full 3D non-LTE treatment, the discrepancy is by far not as large as for the oxygen lines. They come out pretty similar. The NLTE corrections are small. Talking about contribution functions, I didn't show this. This is a contribution function for this lithium line in LTE and non-LTE. I said in LTE, this is the LTE contribution function. I should say the integral of these curves, this is a continuum, this is a non-LTE contribution function, this is the LTE contribution function, as a function of optical depth. The integral of these curves gives the overall equivalent width of the line. And one sees here, from the transition from the LTE to the non-LTE case, that all these contributions from higher layers of low temperature, and where also collisions are rather infrequent, so